Okay, so we are talking about something called colligative properties. Colligative properties are properties of solutions that only depend on concentrations of the particles, not type of particles. So you can have a whole bunch of different solutes in there, and we don't care, if some are ionic and some are molecular, which means covalently bonded. We only care about how much there is the concentration. So when association means coming together, dissociation means breaking apart. Ionic solids breaking apart. Now remember, ionic solids, those are metals plus nonmetals. Okay, so they are going to break apart into their ions. So for example, if you've got metal, I don't know, let's say we have aluminum oxide. So that's going to break apart into its ions. It's going to break apart into aluminum, which is a +3, and oxygen, which is a -2. And then we'd have to account for the number of ions by putting those out there. So see how I broke apart my ionic compound into its ions, and then I counted up the numbers that's there. Things that are covalently bonded are not going to dissociate. So something like, I don't know, NH3. So instead of showing it breaking apart into these two ions, you're just going to say does not dissociate. Now, when you count up the number of ions it breaks apart into, that's something we call the Van Hoff factor. And that Van Hoff factor is simply a number, there's no units, and that helps us figure out, who's going to raise the boiling point the most, lower the freezing point the most a little bit later. So here we have 4 solutes, and let's say we're going to put them all into water and see if they'll dissociate. So the first thing you need to do is say, do you have an ionic solute, which we do. So this first one is a metal and nonmetal. So this is going to break apart into Na and its charge. And if you forgot your charge, it's on periodic table, +1, and Br-. So then you count up your your ions, 1, 2. So your Van Hoff factor is 2. What does that number do for us? Stay tuned. Okay, so then we have another solute, magnesium chloride. So this is, again, an ionic compound. So we're going to break it up into its ions. We have magnesium, which is a +2, and we have Cl, which is a -1. However, notice how we have 2 Cl's here, which means we have 2 Cl ions in solution. So then I count up my number of ions, 1, 2, 3. So what that's going to tell us is when you dissolve sodium bromide in solution and you compare it to magnesium chloride in solution, magnesium chloride has more ions, which means it's going to make the freezing point go lower and the boiling point go higher. It's going to be more extreme due to the number of ions. We don't care that they are different solutes, we just know that there are different numbers of ions. Our next one, we have metal and we have nonmetals in the form of a polyatomic. So if you remember, polyatomics stay together. So you're not going to break that thing apart. You're going to keep that together. But it does have a charge. So as they break apart, we have lithium, which is +1. However, there are 2 of them. And sulfate is a -2 charge, as found on table E. So count your ions. 1, 2, 3. Van Hoff factor is 3. This last one, glucose, is not ionic. This is molecular, which means covalently bonded. And so it will not dissociate. It's not going to break apart into any ions. So instead of writing down, any kind of ions, which it doesn't have, we'll say does not dissociate. However, it's not going to disappear. We're still going to have this chunk. It's not going to break apart any further. So our Van Hoff factor is 1. Van Hoff factor is always going to be 1 for molecular substances, solutes. And there's something called non-electrolytes. We're going to talk more about electrolytes in our next unit, but for right now, you know that electrolytes produce electricity in solution and something molecular will not. So this is Van Hoff factor. It's going to come in handy for our next part here. So freezing point. All substances have a freezing point. Freezing point depression would be lowering of the normal freezing point. When a solute is dissolved, so, let's say we have sodium chloride in water or the magnesium chloride or even that lithium sulfate, it's going to lower your normal freezing point. The amount the freezing point of a solvent is lowered by dissolved substances depends on two factors. One, concentration. If you have a higher molality, which means more concentrated, lower freezing point. So the more concentrated is going to decrease your freezing point more. Electrolytes have a lower freezing point than non-electrolytes. So electrolytes, those are, we're going to talk later, those are acids, bases, and salts, things that are ionic, so ionic solutes. And then later we're going to talk about what an acid is and what a base is. So, for example, a 2 molal solution will freeze at a lower temperature than a 1 molal because it's got more ions. It's more concentrated. More ions are going to lower that freezing point. Okay. So that's the first thing that is going to help us figure out, who's going down the most. That is I wrote on it, salt truck. And so putting down salt on icy roads helps lower the freezing point of that water. It doesn't technically melt the ice because melting is a, addition of heat here, but this lowers your freezing point. But it also depends on the nature of your solvent. So equal amounts of the same solute in different types of solvent will freeze at different temperatures. So again, if we're discussing water as a solvent versus acetone as a solvent versus benzene as a solvent versus alcohol as a solvent versus acetic acid. So it depends on what you're dissolving into. So you can have different solvent. That definitely plays a role. So here's a formula to calculate the freezing point depression. We talked about it qualitatively. Like if you dissolve a solute, your freezing point will go down. But that's qualitative. Let's be quantitative and use numbers. So here we have a formula. It is not on the reference table. And these three things on the right are multiplied. So what are they? So first of all, delta T sub F means the change in temperature, and the F means the freezing point. So the change in the freezing point depression, it's going to equal I. I does not mean imaginary number. I means the Van Hoff factor, which is the number of ions. K sub F is a constant. It is the molal freezing point depression constant. And if we go here, on the honors reference table, you will see for water, it's given. If you are using a different solvent that's not water, it would have to be provided to you in your question, or you'd have to be able to look it up. But for water, the molal freezing point depression constant is 1.86 degrees Celsius, found right here on the honors reference table. Okay, thank you. And lowercase m, of course, is molality. So let's review. That is moles of your solute over kilograms of your solvent. And you just multiply those three things together. And once you get this value, you're going to subtract from the normal freezing point to determine the new freezing point. Okay, so here's a couple molal freezing point depression constants. This is on, I think I have this. Of course I do. Honors reference table A. But here's some other ones. Are you going to need to memorize this? Absolutely not. But these are just some, different constants that you would use if you had a different solvent besides water. Okay, here's a question. How much will the freezing point be lowered if enough salt is dissolved in water to make a 0.5 molal solution? And I'm going to guess this is NaCl. I should have been more specific. Okay, so how much will it be lowered? This is going to be quantitative now. So delta T sub F equals I times K sub F times little m for molality. Okay, so if we have NaCl over here to the side, let's dissociate that. So that's going to be Na plus and Cl minus, which means 2 ions, which means the Van Hoff factor is 2. So delta T sub F is 2. Our molal freezing point depression constant, it's dissolved in water, so we're going to use that 1.86 degrees Celsius. 1.86. And that's, by the way, the Van Hoff factor does not have units, but this is 18.86 degrees C per molal. And then obviously this is molal, so that's going to come out. And that was provided to us, molal. So molal goes away. There are no units for I, so it gives us our temperature. So delta T sub F, let's multiply 2 times 1.86 times 0.5, which you might notice gives us 1.86 degrees Celsius. So how do you figure out how much the freezing point will be lowered? So the freezing point will be lowered 1.86 degrees Celsius. What is the new freezing point? How do you calculate that? You take your normal freezing point, which is 0 degrees Celsius. You need to know that or look it up. Subtract your freezing point depression and get your new freezing point of negative 1.86 degrees Celsius. So it's going to be a little bit lower than normal if you have a 0.5 molal solution, which is not that concentrated. And there's not a ton of ions coming out of solution with that NaCl. However, dissolving a solute will also increase the boiling point. It will elevate it. So some of these notes are going to be very similar to what we've just taken. They're just talking in the opposite direction, extreme. So when a solute is dissolved, it will raise normal boiling point. And guess what it depends on? It depends on concentration. So here we have, this is a sugar solution for making candy. So to make candy, you need to have a lot of sugar, and you need to put it in water, and you need to increase the temperature a lot. And as you add more and more sugar, it's going to raise the boiling point a lot higher than the normal boiling point of water, which would be 100 degrees Celsius. So again, just like the freezing point depression, the boiling point elevation depends on your concentration. So obviously, the higher your molality, the higher the boiling point, because there are more ions. The more ions, the more extreme highs and extreme lows. And those electrolytes, remember those are ionic solutes, which are salts, acids, and bases, which we'll talk more about later. Those are going to have a higher boiling point than the non-electrolytes, which are those covalently bonded molecular things. So again, 2 molal solution will boil at a higher temperature than 1 molal. Here's our formula. Oh, look, it's very similar. Except for now we're talking about boiling point. So instead of sub F, it's sub B. Again, not on the reference table, so you'll have to refer back to this. Those 3 things are multiplied, but it's pretty much the same. So I is our Van Hoff factor. Kb is the molal boiling point elevation constant, which, as you may have guessed, for water is provided here on Honors Reference Table A. So our molal boiling point elevation constant for water is 0.52 degrees Celsius. Again, that's only for a solvent of water. If we have a different solvent, you'll have to be provided that value in a question or you'll be able to look it up. But the formula is pretty much the same. So again, see how we have that on that reference table? And again, do you need to memorize these numbers? No. Do you need to figure out any kind of trend between those numbers? Nope, don't worry about it. Okay, so this question is a little bit different because it's not asking for the boiling point elevation changes. It's actually looking for molality. So we're just going to have to use algebra here, which is no big deal. 13 grams of a non-electrolyte is dissolved in 0.50 kilograms of benzene. The boiling point of this solution has been increased by 0.51 degrees Celsius. What is molality? So delta T sub B equals I times Kb times little m. So in this question, we were given the boiling point elevation constant. I'm sorry, the boiling point change, which is 0.51 degrees Celsius. If it's a non-electrolyte, that means it did not dissociate. So I don't care what it is. I already know the I value. It's a 1. Okay, so benzene, let's go back. Benzene, 2.53 is our boiling point elevation constant. 2.53 degrees Celsius per molal. And we are looking for molality. So all I have to do is multiply these two things together, which should be pretty straightforward. 1 times that. Divide both sides by 2.53. 2.53. And you should get, let's do that. 0.2, and let's talk sig figs here. 3, 2, 2. 2 sig figs. And this will be, you can say mole per kilogram, or you can just say molal. 0.20 molal. Okay, that's not very concentrated. No, I don't want to do this. Okay, so that's pretty much it. So now, hopefully you know, the more solute you add to a solvent, if it's it's going to increase the boiling point, it's going to lower the freezing point. That's qualitative. But if we want quantitative, we need to use these formulas. Okay, thanks.